Welcome to the deep dive. Today, we're going deep into material science and engineering, but with a twist. You've given us some interesting source material here. Um, it goes into economic, environmental, and societal issues surrounding these amazing materials.
Yeah, so we're talking about everything. We're going to talk about the cost of making cool new things to the challenges of even recycling.
That spaghetti-like tangle of composites.
Yeah, exactly. And what's really interesting is we often focus on the really exciting aspects of materials, but there's this whole other layer of considerations that engineers grapple with on a day-to-day basis, right? It's like this balancing act between pushing those boundaries of innovation, but also understanding the real-world impact of those choices.
Right, because what good is a groundbreaking new material if it breaks the bank or leaves a huge environmental footprint?
Exactly. So let's start by talking about the economic side of things. The source material actually kicks off by posing this fundamental question. How do engineers juggle making awesome things while keeping costs in check? And it turns out there's three main levers that they can pull: component design, material selection, and manufacturing techniques.
Okay, so it's not just about picking the cheapest material off the shelf. There's a whole strategic dance involved.
Absolutely. Take material selection, for instance. What seems like a simple choice can have a ripple effect on that entire process. It impacts the component design, the manufacturing methods you can use, and even how much waste is generated.
So it's like a giant game of chess where each move has to be carefully considered.
That's a great analogy, and that's why the source material emphasizes the iterative nature of design. Engineers are constantly evaluating, refining, adjusting their approach based on all of these factors, and of course the budget.
So they're like detectives constantly gathering clues and adjusting their approach.
Exactly. And speaking of clues, let's shift gears a little bit and follow that trail to the environmental and societal impacts of materials. The chapter introduces this concept of the total material cycle, which I think really broadens the perspective.
Ah, yes. The source material even had that helpful diagram, figure 22.1, showing the journey a material takes, from raw material extraction to product creation, use, and finally disposal or hopefully recycling.
Precisely. And it reminds us that the Earth's resources are finite. We can't just keep mining and discarding materials without considering those consequences. The concept of efficient resource use throughout this entire cycle becomes crucial.
And let's not forget the energy it takes to create these materials in the first place. The source material points out that about half of the energy used in U.S. manufacturing goes towards producing and fabricating materials. That's a huge chunk.
It really highlights the need to optimize energy consumption at each stage of that cycle. So every step from extracting the raw materials to processing and manufacturing and finally disposal or recycling all leaves an energy footprint.
And those footprints can have some pretty serious environmental consequences, right? Pollution, resource depletion, even ecological damage are all on the table.
You're absolutely right. And the source material doesn't shy away from these issues. For example, it highlights the energy savings of recycling aluminum cans compared to refining new aluminum. So it's a powerful example of how even small choices can make a big difference.
So how do companies try to measure and manage these impacts? I remember the chapter mentioned something called life cycle analysis.
Yeah, life cycle analysis is a really powerful tool that allows companies to assess the environmental impact of a product throughout its entire lifespan, from its creation to its eventual disposal, or as the chapter puts it, from cradle to grave.
So it's like giving each product an environmental report card.
That's a good way to think about it. And it's becoming increasingly important as consumers become more aware of sustainability and demand more transparency from the companies they buy from.
Figure 22.2 from the source material really helped me visualize this. It shows those inputs, materials and energy, and outputs, the waste, at each stage of the product life cycle. Really drives home that point that everything is connected.
Now let's zoom in a little bit and take a closer look at the specific recycling and disposal challenges we face with different types of materials. So we're talking metals, glass, plastics, rubber, and those wonderfully complex composites. Each one has its own story to tell when it comes to recycling and its impact on the environment.
Let's start with metals. They seem like they should be easy to recycle, right?
You would think so, but it's a little more nuanced than that. Metals have varying degrees of recyclability and even biodegradability, which might sound surprising. So some metals are highly recyclable, while others are much more difficult to process. Then there's the issue of corrosion, which can impact both their recyclability and their biodegradability.
And of course, we can't forget about those toxic metals that add another layer of complexity to the whole recycling equation.
Absolutely. That's why designing products for easy disassembly is becoming crucial. If you can easily separate different types of metals from a product, it makes recycling much more efficient and less impactful.
Okay, metals are tricky. What about glass? It seems like it should be a recycling superstar.
You'd think so, right? Glass is inert and doesn't biodegrade, which means it sticks around for a long time. And while recycling glass is technically possible, it's not always economically viable. Sorting different types and colors of glass can be time-consuming and costly.
So even with a material as seemingly straightforward as glass, there are economic realities to consider.
Exactly. But the chapter does point out some benefits to using recycled glass, things like faster production rates and reduced emissions compared to making new glass from raw materials.
All right, let's move on to the stars of the show, plastics and rubber. They're everywhere, but their durability also makes them a recycling nightmare.
It's the classic double-edged sword. You know, their very properties, durability, and resistance to degradation make them fantastic for so many applications. But they also make them a huge environmental challenge when it comes to disposal.
The source material does a nice job of explaining the difference between thermoplastic and thermoset polymers in terms of recycling. So thermoplastics can be melted and reshaped, making them easier to recycle. But thermosets, with their cross-link structures, are much more difficult to deal with.
And then there's the ever-present problem of discarded tires. Mountains of tires just sitting in landfills, not breaking down. It's a major environmental headache.
Speaking of headaches, let's tackle composites. They're amazing materials, but recycling them seems about as easy as unmixing a cake.
You're not wrong. Composites are inherently difficult to recycle because they're made of multiple materials blended together. Trying to separate those components for recycling is a real challenge.
Yeah, it's definitely an area where more research and innovation are needed. The source material does mention some emerging techniques for recycling composites, but they're still in those early stages and face limitations. It's kind of a frontier in material science, and finding solutions is going to be crucial.
Okay, so we've covered a lot of ground here, from the economics of material choices to those recycling challenges of various materials. Now let's dive into a topic that's been generating a lot of buzz: biodegradable polymers.
This is where things get really interesting and potentially a bit controversial. The source material even hints at some early excitement and disappointments with biodegradable plastics back in the 70s and 80s, so it seems like there's a history here.
Yeah, it's like the idea of biodegradable plastics had its own little roller coaster ride of hopes and setbacks. So, before we get into all of that, let's just break down what biodegradable polymers are and how they actually work. So, at their core, biodegradable polymers are designed to break down naturally in the environment, mainly through the action of microorganisms. Think of it like a microscopic composting process, These tiny organisms essentially eat the polymers, breaking them down into smaller, more digestible pieces.
So it's nature's own recycling crew. And the source material actually mentions some natural examples of biodegradable materials we're all familiar with, things like wool and cotton. It's a good reminder that nature has been doing this for a long time.
Absolutely. But, creating synthetic biodegradable polymers is a bit more complex. And as the chapter points out, those early attempts in the 70s and 80s didn't quite live up to the hype. They didn't degrade as quickly as hoped and led to some disillusionment with the whole concept.
So it's like they had a great idea, but the execution wasn't quite there yet. What changed?
Well, the industry kind of learned from those early setbacks, right? They developed standards to accurately measure degradation rates and characterize how these materials break down. And this led to kind of a resurgence of interest in biodegradable polymers. But the focus shifted towards more niche applications where their shorter lifespan is actually an advantage.
The source material gives a great example of this with mulch films used in farming. Those plastic sheets that help protect crops and extend the growing season?
Exactly. Traditionally, those films were made from non-biodegradable polyethylene, which meant farmers had to collect them at the end of the season and figure out how to dispose of them. But now there are biodegradable mulch films that simply break down into the soil after they've served their purpose. It's a win-win for the farmers and the environment.
It's a fantastic example of how understanding the properties of a material can lead to a much more sustainable solution. The source material also mentioned the potential of biodegradable polymers in the fast food industry. Imagine a world where all those disposable cups and containers could just be composted along with our food waste.
It's an exciting prospect. And, it could significantly reduce the amount of waste going to landfills. But the chapter does make it clear that there's a key distinction to understand when we're talking about biodegradable polymers. Biodegradability doesn't always mean they'll just disappear overnight. Some require specific conditions, like those higher temperatures found in commercial composting facilities, to actually break down effectively.
So it's not quite as simple as tossing your biodegradable coffee cup in the backyard and watching it magically decompose.
Not quite. But the potential of these materials is still immense, especially as we look for ways to reduce our reliance on traditional petroleum-based plastics.
And speaking of reducing our reliance on petroleum, let's talk about another key concept from the source material biorenewable polymers. These are materials that are sourced from plants rather than fossil fuels, right?
That's right. Biorenewable polymers are derived from biomass, meaning anything that comes from plants or other organic matter. It's a way to create more sustainable materials that don't contribute to our dependence on fossil fuels and, the associated greenhouse gas emissions.
Okay, that sounds promising. But are these materials strong and durable enough to replace traditional plastics?
Well, the source material highlights a particular biorenewable polymer that seems to be making waves in that regard. Polylactic acid, or PLA for short. PLA is gaining popularity because it has properties that make it a viable alternative to traditional plastics. So, for example, it's comparable in strength and stiffness to peat tea, which is commonly used in beverage bottles, and it can be processed using a lot of those existing manufacturing techniques. Plus, it's transparent, so you can still see what's inside that PLA-based packaging.
So it's like the biorenewable cousin of peat, but with an eco-friendly twist. What else makes PLA so appealing?
Well, aside from those properties, PLA is also bioresorbable, meaning it can be safely broken down and absorbed by biological systems, even the human body.
Wow, so it just eventually disappears.
Yeah.
That's amazing.
Yeah, it is. And that characteristic opens up some incredible possibilities in the medical field. Imagine using PLA for resorbable sutures that dissolve after surgery, implants that don't require a second procedure to remove, or even for controlled drug delivery, where the material gradually releases medication within the body.
Those are some game-changing applications. But I'm guessing there are challenges to overcome with PLA, right? Nothing's ever that simple.
You're right. The biggest hurdle, as the source material points out, is cost. PLA is still more expensive to produce than traditional petroleum-based plastics, which hinders its widespread adoption. But researchers are constantly working on developing, more efficient and economical production methods, so the future looks pretty promising.
It's like a race against time to find sustainable solutions that can keep up with our modern demands.
Exactly. And speaking of time, there's a common misconception about PLA that the chapter addresses head-on. People think that it only degrades under very specific conditions. And while it's true that PLA won't magically decompose on your kitchen counter, it does break down readily in commercial composting facilities, where temperatures are higher, so proper disposal is still key.
So it needs a little help from the right environment to do its disappearing act. But overall, it sounds like PLA has a pretty bright future ahead of it.
Indeed. The chapter concludes by emphasizing PLA's versatility and its potential for a wide range of applications, from packaging to even textiles. It's definitely a material to watch.
This has been a fascinating deep dive into the world of materials. And it's clear that there's this constant push and pull between innovation and economics and sustainability. It's not just about creating cool new stuff, it's about understanding the full impact of our choices.
Right, and it seems like we can't escape those trade-offs, but maybe that's where green design comes in. The source material touched on that concept. Is that kind of the key to finding a better balance?
Yeah, green design is definitely a crucial part of the solution. It's a shift in thinking from simply minimizing the negative impacts to actually actively seeking out ways to create products and processes that are beneficial for the environment. It's that proactive approach that goes beyond just doing less harm.
So it's like turning the challenge into an opportunity. Like, how can we make materials and products that give back to the planet?
Exactly. And engineers are really at the forefront of this whole movement, developing new materials and processes with that sustainability baked right in from the start. But it's not just about the scientists and engineers coming up with these innovations, right? It's also about the consumers embracing these changes.
That's a good point. What can we as consumers do to kind of promote the use of more sustainable materials? Recycling is the obvious answer, but it feels like there's more to it than just tossing our plastic bottles in the blue bin.
Right. You're right. Recycling is important, but it's only one piece of the puzzle. And the source material kind of encourages us to think beyond just recycling and consider other actions that can truly make a difference. Like, for instance, we can make conscious choices about the products we buy, opting for those made from sustainable or recycled materials.
Right, so voting with our wallets.
Yeah. Sometimes it feels like just a drop in the bucket. But, when enough people make those choices, it can send a really powerful signal to those companies.
Absolutely. Don't underestimate the power of consumer demand. When companies see that people are willing to pay for those sustainable products, they're much more likely to invest in actually developing and producing them. It creates this positive feedback loop.
So we're not powerless in all of this. We can actually drive change by making informed choices.
Exactly. And that brings us to kind of a thought-provoking question I think is worth pondering. Given everything we've discussed, what role do you think consumers play in driving the development and adoption of more sustainable materials? It's something to think about as you go about your day.
That's a great question to leave our listeners with. It's a reminder that we all have a part to play in shaping a more sustainable future. Well, we've reached the end of our deep dive into the world of materials, science, and engineering. It's been quite a journey exploring the intricate web of economic forces, environmental impacts, and those societal implications of the materials we rely on every single day.
It's been a pleasure joining you on this exploration. Remember, even those seemingly simple choices can have a huge ripple effect. So keep asking questions, stay curious, and keep diving deep into the world around you.